Hello everybody, we got a problem here in basic mechanics to solve. And this problem, we are given two wedges, each of mass small m. These are the wedges, this one and this one. They are placed next to each other on a flat floor. A cube of mass capital M here, this one is the cube. This cube is balanced on the wedges as shown in the figure. Assume no friction between the cube and the wedges, but a coefficient of static friction mu less than 1 between the wedges and the floor. What is the largest mass of the block, capital M, that can be balanced as shown without motion of the wedges? And our answer should be one of these five answers: A, B, C, D, and A. Now guys, the first thing to note here in this problem is this. According to the symmetry of the problem, the two wedges shown here are pushed sideways equally, with forces of the same magnitudes that are provided by the weight of the block. And balancing the largest mass m of the block means that a wedge is on the verge of sliding, which would mean that a horizontal push provided by the block to a wedge should be balanced by an opposing frictional force between that wedge and the floor. So in this problem, we need to find out these two forces. That is the horizontal push on a wedge by the block and the force of static friction between that wedge and the floor, and then equate them. I have redrawn the figure here to show the forces involved explicitly. Here, this capital M times G is the weight of the block, and here I have resolved this force into two rectangular components. Say this one is A, which acts on wedge A here, and the component B, which acts on wedge B, say here. And both these forces should be equal in magnitude, as you can prove it very easily. This angle should be 45 degrees, and this angle should also be equal to 45 degrees by symmetry of the figure. Now, vector A has a magnitude equal to, let us write the magnitude as A. This is equal to mg times cosine of 45 degrees, which is equal to, cosine 45 degrees is equal to 1 by 2 under the root. So this is equal to m times g divided by 2 under the root. Similarly, vector B also has the same magnitude. If you bring this vector B here, so from this triangle, you will have vector B equal to, the magnitude of vector B equal to mg times sine of 45 degrees, which is also equal to 1 by 2 under the root. So this is equal to mg divided by 2 under the root. Since the situation is symmetric with respect to wedge A and B, consideration of either one of them will suffice to solve the problem. So let us consider wedge A. Now let us find out what are the forces acting on wedge A, which essentially are coming from the block of mass M. So one is this force, which is the rectangular component, the horizontal component of the vector A, and the other one is this one, which is the perpendicular component of vector A acting downward on the wedge. So what are the magnitudes of these vectors? Let us call this one as AX component, which is actually responsible for pushing the wedge A to the right. And one is this one, you call this as AY. Now let us find out their magnitudes. Vector AX has magnitude. Now remember, this angle again is equal to 45 degrees. So vector AX has magnitude equal to, let me write it here. AX has magnitude equal to the magnitude of A times cosine of 45 degree. Now the magnitude of A is equal to mg, this value, mg divided by 2 under the root times cosine for 45 degrees, so which is 1 by 2 under the root. So this is equal to mg divided by 2. Similarly, ay, magnitude of vector ay is equal to a times vector a times sine of 45 degree, because it is perpendicular, 45 degrees, which is now equal to vector A has magnitude mg divided by 2 under the root and multiplied by sine 45 degrees, which is again 1 by 2 under the root. So this is equal to m times g divided by 2. Now the mass or weight of the block is such that wedge A is on the verge of sliding. This means that beyond this value, wedge A will start sliding. So when wedge A is on the verge of sliding, the horizontal force acting on wedge A, which is coming from the block, here it is AX, the magnitude of this force should be equal to the magnitude of the opposing frictional force acting on wedge A and coming from the floor. We denote it by Fs. So let us equate the magnitudes of these forces acting on the wedge A. So let us first write down the magnitude of the static frictional force Fs. It is equal to mu times the normal force N acting on the wedge. And this normal force is a reaction force on wedge A here. It is the normal force, and then the magnitude of this normal force is equal to the sum of the magnitudes of the forces acting on wedge A downwards. So the downward forces on wedge A are, one is its weight mg here, and the other is the force Ay coming from the block. So let us write it down here. It is equal to mu times mg plus the magnitude of Ay. Here it is mg divided by 2. So mg divided by 2. And this should be equal to Ax. Now the magnitude of Ax is equal to mg by 2 here. So equate this value here to mg by 2. So let us write it down here separately. Mu times mg plus mg divided by 2 is equal to mg divided by 2. This is the magnitude of Ax. Now from here, from this equation, you can simplify this into, if you bring this there, so this is equal to mu mg is equal to, bring that there, so, and take mg by 2 common from there, so you will get here 1 minus mu. And from here g and g cancel out here, and you are interested in the value of capital M here, so just bring this 2 here and 1 minus mu down. So M here will be, capital M will be equal to 2 times mu M divided by 1 minus mu. And this is the correct answer. Here it is answer D. So answer D is the correct answer. Thanks for watching, guys.